Welcome back. In today's video, we're going to begin discussing limits, which we're going to have a lot to say about. But it turns out we've already done one limit, and so I want to talk about limits in the context of the one limit we'd already done 2 videos ago. Namely, 2 videos ago, when we were trying to find the equation of that red tangent line, we found ourselves looking at the quantity 16 minus a squared divided by 4 minus a. And what did we want? We wanted to plug in a equals 4. But we had this problem that if we did plug in a equals 4, then we got 0 over 0. And that was super unhelpful. So what did we do? We said, oh, well, hey, if I factor this, it'll be 4 minus a times 4 plus a divided by 4 minus a. Cancel those. This is 4 plus a. And now, if we plug in a equals 4, we get 8, which is the thing that we wanted. I want to figure out what mathematically is really going on here. And in order to do that, I want to think about what happens when I graph the function f of x equals 16 minus x squared divided by 4 minus x. All I've done here is change the a's to x's and put it in function notation so that we can talk about the graph. Okay. And it seems like because of this string of equal signs here, that this is just 4 plus a, so this would just be 4 plus x, so I'll put an equals with a question mark over it. And so you're probably inclined to think, okay, well this graph here, it ends up looking like a line with a positive y-intercept, so it'll end up looking something like this. And you would basically be right, except for one thing, which is that there is one crucial difference between the thing on the left and the thing on the right. And what's the crucial difference between the thing on the left and the thing on the right? It's the magic 4. If I plug in 4 to the thing on the left, it's undefined. If I plug in 4 to the thing on the right, it's 8. And the way that shows up in the graph is that there's a hole in it. Namely, if I graph the thing on the left, I end up with, at the input 4, rather than getting 8, I get nothing. But the y-coordinate of this hole is still very much 8. So what happened before? What happened when we rewrote this? We basically found the location of this hole. And one way to think about what we're doing is instead of looking at the exact input 4, we're looking at inputs near 4. Okay. And at inputs near 4, the value of this function, f, is really, really close to 8. For example, if you choose your favorite number near 4, like, for example, 4.002, then this function f, it legitimately does take the value 8.002, which is very close to 8. The only problem, again, is that f of 4 itself, which has the annoying property of being the value we actually want, this is undefined. So are these two things really equal? Not quite. I wouldn't complain if you said they were, but they're not quite exactly the same thing, and the reason why they're not quite exactly the same thing is that I can plug 4 into the thing on the right, but not the thing on the left. Okay. So arguably what that means is the thing on the right is different because it's better. I can plug in 4 and not worry about it. The whole idea of limits exists for the purpose of dealing with this kind of hole. Okay. That is, the purpose of limits is to allow you to quote-unquote evaluate a function at a point where the function is undefined. Okay, so let me write the calculation that we did before in the new notation. Namely, I want to plug a equals 4 into 16 over a squared divided by 4 minus a. The way I'm now going to write that is as the limit as a goes to 4 of 16 minus a squared divided by 4 minus a. And really, you should think of this as saying, I want to plug in a equals 4, but I suspect there's a problem. But once we have this technology, we're going to be able to say, this is equal to 8. And this is even though f of 4, that is our function where we just try and directly plug in 4, is undefined. Okay, that is the whole point of limits. So, how are we actually going to define what this business with a limit means? Namely, when I write something like the limit as x goes to c of some function f of x, okay, so notice here x is the input of some function, and this arrow is saying I want the input to be c. But I'm going to accept that maybe this function's not defined at c. Okay, so for example, back here, when we were looking at this function and we wanted the limit as x went to 4, that would be our c, then the output was undefined. But nonetheless, this 8 was sort of baked into this. Okay. And how did we really get to this 8? We looked at inputs near 4. So that's the key. That's the secret to how we're going to define limits. I'm going to say this is the output that f of x is close to for inputs close to c. And I'm going to say not just close to c, close to, but not equal to c. So, in other words, when faced with a problem like this one, where I want to evaluate this thing at 4, and I can't because it's undefined, the idea of limits is, well, hey, pick some point ridiculously close to 4, like 4.002, and evaluate the thing there, and then maybe pick a few other places that are close to it, and then from those, you can sort of triangulate what the coordinates of this hole have to actually be. Now, I should put a caveat here, namely, I should put the caveat that this is only provided such an output exists. So it's very possible that when I look at inputs near C, that I don't get outputs close to anything, in which case then this limit is just going to be undefined. Before we get into doing more examples of this algebraically, here's a graph of a very weird function. Why is it weird? Well, it's got a hole in it in a few places. It's got this thing that we called a jump before. It's got a jump discontinuity. Its value at -1 is sort of like off here. It has no value at 0. So no function that you've really thought about before would have a graph like this, but this is a perfectly valid function. And I want to make sure that we can read off things from this graph. So let's look at what is f of 2. Well, f of 2 just is 1. Nothing too special to read off here. What's f of 0? Well, f of 0 is undefined because of this hole in the graph, right? I try and find the value here at the input 0. And there isn't one. What's f of minus 1? Okay, and I apologize for this kind of ugly picture. But what is f of minus 1? F of minus 1, remember I read up through the hole, so f of minus 1 is 4. And f of minus 2, that's also 4. Now, all of this we could have done before this section. What I want to do now is compare and contrast these 4 values of the function to the values of the corresponding limits. So, namely, I want to look at what happens when I take the limit as x goes to 2 of f of x. So this is saying, if I plug in values of x very near to 2, but not equal to 2, what output do they end up near? So things like there and like there. Okay. And those outputs, they end up very close to 1. And so this limit is 1. Okay. Now I want to note, I put a solid dot here in the graph. That doesn't mean anything. If I'd omitted the solid dot, it would have been exactly the same. Just putting a solid dot on the graph doesn't change the function that's being described. Okay. So in this instance, the limit and the function actually both give you the same output. It would have been equally easy for me to just say f of 2 if this was the point I wanted. I would have gotten the same thing. Now, what about the limit as x goes to 0 of f of x? So again, now this is talking about inputs that are near 0 but not equal to 0. So we're looking at outputs, again, a little to the left or a little to the right of 0. And if I go a little to the left or a little to the right of 0, what do I end up getting? I end up getting something near 4. This situation, at 0, that's exactly what limits are for. There's a hole in the graph right there, but I can grab the value that sort of the hole should be at by using a limit. So effectively, what this limit is doing is it's letting us fill this hole in and evaluate the function, even though technically the function's undefined there. Okay, so this, again, this is the time we're most often going to use limits, where the function's undefined at a point, but that point is just a hole in the graph, so we can find the coordinates of the hole using limits. How about the limit as x goes to minus 1 of f of x? Okay. So here, f of minus 1 was 4. Okay. But remember what a limit does. Namely, it looks at inputs close to, but not equal to, the input we're talking about. So you might be inclined to say that this situation at minus 1 is a lot like the situation at 2, and so you might be inclined to say, well, f of minus 1 is 4, so this limit should also be 4. But that's not true because of the part about inputs close to but not equal to this. So namely, if I take some inputs close to but not equal to minus 1, there are points like those, which end up here on the graph when I translate those inputs to outputs. And what output are these close to? They're not close to the 4, they're close to the location of this hole, namely, they're close to 3. So what did the limit really do here? It said, well, there's this point off in the middle of nowhere, but it doesn't belong there. That point's really supposed to be here. And so the limit kind of fills in this point and just completely ignores this point. So this point being here or not being here doesn't affect the limit at all. So be careful when you just end up saying to do the limit, you just plug something in. That only works if the function is nice enough that when you plug it in, you get the same value that you're supposed to. Okay, it does not work if you're in some situation like this. Okay, last up, let's look at what happens at -2. Namely, I'm looking at inputs near -2. Okay. And my outputs then end up there and there. And note here, when I'm talking about inputs near -2, I can't only look at the right or only look at the left. I have to look at both pieces. And on the right, I end up over here near 2. Whereas on the left, I end up here near 4. But this is where this caveat at the end, provided that such an output exists, comes up. Here, there is no output that I always end up close to for inputs close to -2, because inputs close to -2 could end up with outputs near 2 or outputs near 4. So this limit is in fact undefined. Now, preview of something we'll talk about in a few videos, we can tell that this limit is really torn between wanting to be 2 and wanting to be 4, and we do have a way of getting at that. Namely, we write something like this, and the key thing I've added here is these little pieces of jewelry, the minus up here and the plus up here. Note that's not the same as the minus down there. The minus down here is telling me, hey, look at -2, not +2. This minus is telling me which side to look at. Namely, this is telling me to look at the left side, the negative direction. So namely, this is telling me, look only at this piece, not at that piece. And so if I come at this from the left, then I end up here. I don't ever end up over here if I'm on the left-hand side or on the negative side. And so this would end up being 4. Okay. And then this limit as x goes to -2 from the right. That will end up over here. If I go in the positive direction, I end up close to this side. And so that'll end up being close to 2. And so in the instances where you have sort of something happening on the left and something happening on the right, but they don't match, then we're going to talk later about using these sort of one-sided limits, as they're called, to sort of separate out those two things. But you get this problem at these sorts of jump discontinuities that we've been talking about now and then. I'm going to wrap up this video here. In the next video, we're going to start talking about limits coming from functions written algebraically. That is, ones written with x's and that sort of thing. We'll talk about where those come from. But that's all for now. I'll see you next time.